Good day everyone, we are the group 6 of grade 12 de San Vitores, and here we are going to present our output for the collaborative work in physics. The main objective for this video is to apply the concepts and share our knowledge from the subject journal Physics 1 by solving world problems of the lessons Work in Kinetic Energy, Potential Energy, and the Law of Conservation of Mechanical Energy. Now without further ado, let us start with the first problem.
A 12-kilogram package in a male sorting room slides 2 meters down a chute that is inclined at 53 degrees below the horizontal. The coefficient of kinetic friction between the package and the chute surface is 0.40. What is the net work done on the package? First, let us have the free body diagram, or the FBD of this problem. Now that we have that, we can now understand the concept of this problem more. As you can see, this word problem is an example of the work energy theorem, and in order to solve this, we need to follow these steps. In order for the net work done on the package, we need to find the sum of friction, gravity, and normal force. In other terms, we need to use the formula W net is equal to Wf plus Wg plus Wn. In order to do that, we need to first solve the work done by friction, next is to solve the work done by gravity, and lastly, solve for the work done by the normal force. Now before we start solving, we should first follow the GRS format, or the given, required, and solution format. First, the given. We have 12 kilograms, which is our mass, 2 meters, which is our distance, an angle of 53 degrees, and lastly, the coefficient of kinetic friction between the package and the chute surface, which is 0.40. Now that we have our given, we must identify what is required for this problem, and that is the net work done on the package. First, part of the problem is to solve the work done by friction. So to solve the work done for friction, we're going to use the formula Wf is equal to negative mu kx ng cos sine theta, where we multiply negative mu k, which is our coefficient of kinetic friction, mass, gravity, which is a given value of 9.8 meters per second, cosine theta as our angle of inclination, and our distance all together. So with our given data, we input it like so in our formula, and now we have the answer of negative 56.62 joules. Second part is to solve the work done by gravity. Next is to solve the work done by gravity, we will utilize the formula Wg is equal to mgx sine theta, where we multiply our mass, gravity, sine theta, and distance all together. With our given data, we input it like so in our formula, and now we have the answer of 187.84 joules. Third part is to solve the work done by the normal force. Lastly, to solve the work done by normal force is automatically equivalent to 0 since the normal force is perpendicular to the displacement. Now that we have the values of work done by friction, gravity, and normal force, we can now find the total net work done on the package. So W net is equal to the total sum of the values of work done by friction, gravity, and normal force. We input our given, and now we have 131.22 joules as our answer. Finally, we have the answer for our first problem. The net work done on the package is 131.22 joules.
Next problem. A 4.8 kilogram watermelon is dropped from rest from the roof of an 18.0 meter tall building and feels no appreciable air resistance. Calculate the work done by gravity on the watermelon during its displacement from the roof to the ground. Firstly, let us have the free body diagram, or the FBD, of this problem. Before we start solving, we should first follow the GRS format, or the given, required, and solution format. First, the given. We have 4.8 kilogram, which is our mass, and 18.0 meter, which is our height. Now that we have our given, we must identify what is required for this problem. And that is the work done by gravity from the roof to the ground. Lastly, now that we have identified our given and what is required, we can now start solving this problem. For this problem, we are going to utilize the formula for the work done on the mass, which is W equals Ft equals mgh, where m is our mass, g is our gravity, with a given value of 9.80 ms, and h as our height. With r given, we input it like so to our formula, which yields 846.72 joules. Finally, we have the answer for our second problem. The work done by gravity on the watermelon during its displacement from the roof to the ground is 846.72 joules.
A spring of negligible mass has a force constant K equals 800 N over M. How far must the spring be compressed for 1.20 joules of potential energy to be stored in it? Firstly, let us have the free body diagram or the FBD of this problem. Now that we can visualize our problem, we can now proceed on the solving part. The main concepts required to solve this problem are spring force and potential energy. Again, before we start solving this problem, we should first follow the GRS format or the given, required, and solution format. First, the given. We have a force constant K, which is 800 N over M, and 1.20 joules as our potential energy. Now that we have our given, we must identify what is required for this problem, and that is the value of x, or the distance the spring must be compressed for 1.20 joules of potential energy to be stored in it. Lastly, now that we have identified our given and what is required, we can now start solving this problem. The expression for the potential energy stored in a spring when it is not in its equilibrium state or unstretched state is as follows. UEL is equal to 1/2 kx squared. Here, k is the spring constant and x is the compression or elongation in the spring. However, in this problem, since we are looking for the distance, we need to rearrange the expression to look for x. Now that we have this, we can substitute our given formula and solve it like so, which gives us the answer of 0.05477 meters. Finally, we have the answer for our third problem. The distance the spring must be compressed for 1.20 joules of potential energy to be stored in it is 0.05477 meters.
Let us now head on to problem number 4. A 1.50 kg snowball is fired from a cliff 12.5 meters high. The snowball's initial velocity is 14 meters per second, directed 41 degrees above the horizontal. Using conservation of mechanical energy, calculate the speed of the snowball as it reaches the ground below the cliff. Firstly, let us have the free body diagram or the FBD of this problem to visualize. Now that we have this, let us proceed. Again, before we start solving, we should first follow the GRS format or the given, required, and solution format. First, the given, we have 1.50 kg as our mass, 12.5 meters as our height, initial velocity which is 14 meters per second, and 41 degrees as our angle of projection. Now that we have our given, we must identify what is required for this problem, and that is to calculate the speed of the snowball as it reaches the ground below the cliff. Lastly, now that we have identified our given and what is required, we can now start solving the problem. Since no external force is doing work on the system, the mechanical energy of the snowball will remain conserved during the course of motion. After using the principle of conservation of mechanical energy, we get the following equation, which is 1/2 mv1 squared plus mgy1 is equal to 1/2 mv2 squared plus mgy2. Since we're looking for a speed or a v2, we need to rearrange our equation and we get 1/2 mv1 squared plus mgy1 is equal to 1/2 mv2 squared. We automatically discard mgy2 since our y2 or our second height is not given in the problem, hence it automatically becomes 0. And if we try to multiply it with our mass and gravity, we also get 0. Since we need to isolate v2 from the rest, we need to multiply both sides of the equation by 2 to get rid of 1/2. We cancel 1/2 from the first variable and add 2 to the other. Next is to divide both sides with m for v2 squared to remain. We cancel m on the first and second variable accordingly.
Lastly, to get rid of the power, we need to add square root on both sides of the equation, leaving us v2. With that, we now have this equation. v2 is equal to the square root of v1 squared minus 2gy1. Now that we have this, we can substitute our given formula and solve it like so, which gives us the answer of 21 meters per second. Finally, we have the answer for our fourth problem. The speed of the snowball as it reaches the ground below the cliff is 21 meters per second.
Now for our last problem. An 80-kilogram skydiver jumps out of a balloon at an altitude of 1,000 meters and opens the parachute at an altitude of 200 meters. A. Assuming the total retarding force on the diver is constant at 50 newtons with the parachute closed and constant at 3,600 newtons with the parachute open, find the skydiver's speed when he lands on the ground. B. Do you think the skydiver will be injured? Explain. And C. At what height should the parachute be opened so that the final speed of the skydiver when he hits the ground is 5 meters per second? First, before we start solving the problem, let us have the free body diagram or the FBD so we could visualize. As you can see, we have the skydiver with a mass of 80 kilograms, our initial height which is 1,000 meters, and our second height which is 200 meters. Next, before we start solving, we should first follow the GRS format or the given, required, and solution format. First, the given, we have 80 kilograms as our mass, y1 or our first altitude which is 1,000 meters, our y2 or our second altitude which is 200 meters, f1 which is 50 newtons, and f2 which is 3,600 newtons. Now that we have our given, we must identify what is required for this problem, and that is for part A, to find the skydiver's speed when he lands on the ground, assuming the total retarding force on the diver is constant at 50 newtons with the parachute closed and constant at 3,600 newtons with the parachute open. Part B, find if the skydiver would be injured. And lastly, calculate the height of the parachute to be opened so that the final speed of the skydiver when he hits the ground is 5 meters per second. Now that we have identified our given and what is required, we can now start solving part A. For this problem, we are going to use the formula 1/2 mv1 squared plus mgy1 plus work other is equal to 1/2 mv2 squared plus mgy2 plus work other. In this formula, v1 is denoted as our initial velocity, which is automatically defaulted as 0 meters per second. y2 is denoted as our final height with a value of 0 meters because he is yet to land. And lastly, the work other will be gravity, considering that the skydiver will leave his initial position as he jumps. With this, we have our new formula, which is mgy1 is equal to 1/2 mv2 squared plus f1x1 plus f2x2. Again, since we are solving for v2, we need to rearrange our formula in order to solve for the speed. With that, we now have this rearranged formula. And since we need to isolate v2 from the rest, we need to multiply both sides of the equation by 2 to get rid of 1/2, and divide both sides with m for v2 squared to remain. Lastly, to get rid of the power, we need to add square root on both sides of the equation, leaving us v2. With that, we now have this equation. To solve, let us input our given first and solve accordingly. And after calculating the equation, we now have v2 is equal to 24.49 meter per second. Finally, we have the answer for part A. The skydiver's speed when he lands on the ground is 24.49 meters per second. Next, let us head on to part B. With a speed of 24.49 meters per second when the skydiver lands on the ground, is he going to be injured? The answer would be yes, because the speed of 24.49 meters per second is greater than the speed of safety, which is only 7.6 meters per second. Lastly, for part C, we must calculate the height of the parachute to be opened so that the final speed of the skydiver when he hits the ground is 5 meters per second. To solve this problem, we are going to use the same formula, which is mgy1 is equal to 1/2 mv2 squared plus f1x1 plus f2x2. In this formula, x1 is denoted as the displacement from the balloon to the height before the parachute opens, and x2 is the displacement from the height the parachute opens until the ground. In this case, both values are not given. However, as x1 is equivalent to the initial height minus x2, we will only get the value for x2 because x1 is dependent on x2. To solve, let us input our given first and replace the value of x1 to y1 minus x2 because just like what I have said, x1 is equivalent to the initial height minus x2. After inputting the given, we now have this. And after calculating the equation, we now have 784,000 is equal to 1,000 plus 50,000 minus 50x2 plus 3,600x2. We solve the like terms first, which gives us 784,000 is equal to 1,000 plus 50,000 plus 3,550x2. And since we are solving for x2, we isolate it from the others. And now we have 784,000 minus 1,000 minus 50,000 is equal to 3,550x2. Now we solve it accordingly. And now we have our answer, which is x2 is equal to 206.5 meters. Finally, we have the answer for part C. The height of the parachute to be opened so that the final speed of the skydiver when he hits the ground is 206.5 meters. And that's it for our video. We hope that you learned a lot from our presentation and may this be helpful for students who are also studying general physics like us. Thank you and have a nice day.